for more than one particle. So if we had, if we have two particles, say particle 1 and 2, and suppose they have Hilbert spaces H1 and H2, and the combined Hilbert space for both particles will be some total H that will be H1, and then there's this symbol here is called a direct product. Okay, so this is a new symbol. Probably haven't seen it before, but these are two separate spaces for the particles. So, for example, if we have spin 1/2 particles, then H1 can have a basis could be Z plus and Z minus, for example, and the second Hilbert space will give a basis that's now Z plus 2, Z minus particle 2. Okay, and the Hilbert space, the total Hilbert space is this direct product. So a state in the total Hilbert space is a direct product of the independent particle states and it can also be linear combinations of those states. Okay, so the states in the total Hilbert space are Z plus 1 cross Z plus 2, Z plus 1 cross Z minus 2, Z minus 1 cross Z plus 2, and Z minus 1 cross Z minus particle 2. Okay? So these would be the states that are available in the combined Hilbert space. So a ket is given generally by, for example, I could have C plus plus, let's just call it C1 2 plus some C2 Z plus 1 cross Z minus 2 plus C3 Z minus 1 cross Z plus 2 plus C4 Z minus 1 cross Z minus 2. Okay? So that would be a general ket for the two-particle system. And alternate notations here there are many, so it's cumbersome to write this, and so we can simplify this by writing things like Z plus is Z plus 1 cross Z plus 2 and so on. So Z plus Z minus could be this, for example. Okay, oh, and you'll also see, you can also see things that are written like this. Okay, where you just drop the direct product sign. Okay, so to emphasize this again, then the Hilbert spaces are independent. We just take direct products, so that each particle can be thought of as completely independent in terms of the Hilbert space here, and we just mash them together to create this larger Hilbert space in this direct product space. Now, when we operate, if we have operators, operators are also segregated into their respective Hilbert spaces. So operators are also written in direct product form. So if I have an operator A that lives in the total Hilbert space H, then A can be written as some A1 cross A2, where if we operate with A on, say, Z plus direct product with Z minus, then I have A is this direct product of operators. So A1, the one on the left, is associated with Hilbert space H1, and it operates only on the first ket, and A2 would operate only on the second ket. So this would be equal to A1 Z plus A2 Z minus.
So is the Z plus in Hilbert space 1 and Z minus in Hilbert space 2, or is it a general thing? Because you didn't label those like you did the other ones.
Yeah, I mean, if I don't label it, the first one is in the first space, the second one is in the second space.
Good to know.
Okay, other questions? About this? Okay. So we can, if we have we can do things like we can write the ket for the first particle. We can change bases in anytime we want. That's just our freedom. So, so if we were to change bases, say, suppose we have the state Z plus tensor or direct product Z minus. Okay, so we have, this is in Hilbert space 1 and this is in Hilbert space 2. Then we can write Z plus 1 is just using what we know. We can write it in the X basis like that, and just stick it in our direct product. Okay, so then we can, the direct product distributes over the plus. And so what we have is 1 over the square root of 2, and then we've got x plus in the first Hilbert space cross z minus 2 plus x1 minus, sorry, x minus 1 direct product z minus 2. Okay, so that's the same state. And so if we were to take now let Sx, let's see, let S1 x hat operate on this state. Well, S1 x hat operates on, this is just the same formulas that we've always had. So plus minus here is plus minus h bar over 2, x plus minus 1. Nothing's sticking a label on it. And so then this would be, we would have 1 over the square root of 2. We would have h bar over 2. Okay, so all of the operations that we've done before they just go through the same way they always have. But, now this thing only operates, if we operate on this direct product ket, then it's the first, this thing lives in the first Hilbert space, it only operates on that first state ket. Okay. Okay, any questions just about the setup here?
I'm just wondering how you do it, which I think we'll get to.
Do what?
Well, so like what makes it a direct product and not a dot product or a cross product? We haven't gotten to that yet, I don't think.
Well, so it's it's a good question. It's not a dot product takes you from takes 2 objects from a vector space and takes you down to the real numbers.
Okay.
And a cross product in a vector space takes you from 2 objects in the vector space to another object in the vector space.
Mm-hmm.
This thing is just, this direct product is just meant to just indicate that the Hilbert spaces are separate. There's
Okay.
nothing more to it. There's not an operation really.
Oh,
I mean, it's really just to, separate them out.
I see.
Okay, so, what we want to eventually get to, which we're not gonna do it just yet, but, for our two particle space, we want to write the basis kets for our combined Hilbert space H in terms of S1, M1, S2, and M2. Okay, these are going to be our angular momentum eigenstates. So where this is the total, this will be the total spin of one. Let me rewrite this up here, so we have some space. Okay, this is, total spin of part one. This is the spin projection, the Z projection. Of spin for particle one, and then the same thing for S2 and M2. Okay, so we wrote those before because that was another way for us to write the basis kets of our Hilbert space. So instead of doing it in terms of Z plus and Z minus and those kinds of things, we wrote it in terms of J and M. But in this case, we have two particles, so but we're just going to change calling this thing S instead of J. But that's all we're doing here. We want to find what the kets are in terms of the angular momentum eigenstates. Okay, so so the spin operators for each particle are S1 hat, which will be, now this is the X component. So S1X, S1Y, and S1Z. Oh, sorry. This is, no, that's right. And S2 here is S2X, S2Y, and S2Z. Okay, so we have a whole other set here of operators to deal with in our two-particle system, so a little bit more complicated than the last time, but not much. So let's look at a physical problem. Where we can use what we've just written down here, and that's just a hydrogen atom. So here we have, particle one could be the proton, and particle two, the electron. And so, let's look at the three sort of, let's see, how do I want to say this? There's sort of three levels of precision that we can look at the hydrogen atom. And the first one is just to ignore spin altogether. So we'll just ignore everything that we wrote down. And here you just have a potential, you have a central potential that's just minus E squared over R. And this gives a quantum mechanical calculation, which we'll do later. Gives the ground state energy of minus 13.6 electron volts. Okay, that's the ionization energy of the hydrogen atom. So if we just ignore everything else, that's all you really get out of. You get the energy levels in the hydrogen atom, but you don't get any of the other structure. So when quantum mechanics first was being developed, the thing that they really did all of their tests and everything on, making measurements and then comparing them to calculations was in atomic physics. And the second one was called the fine structure. And that's where, this is the one where you take into account, so you've got the proton here, the electron is going around, there's a B field from the relative motion. Okay, so you can, from the electron's perspective, the proton is going around it in a circle. If you just consider the planetary picture here, and so you're going to have a magnetic field in where the electron is, and so if you've got your electron here with some spin, it's going to feel a magnetic field, and then so E here is minus mu dot B. This is the same thing that we wrote down for looking at magnetic resonance. And so there's two, there's a splitting in the field. So you can have, with the field and against the field, and then you've got some delta E here. This is like the splitting of sodium lines. So if you look at this, sodium lamp, and you disperse the light with a prism, and you look very closely at the emission lines of sodium, you'll find that there's two right next to each other, and that splitting is due to this. It's due to the fine structure of the atom. Okay, and then there's the hyperfine. And here the Hamiltonian this is some amplitude, let's give it 2A over h bar squared. And then this is, we'll have the interaction of the magnetic moments of the two particles themselves. Okay, so this is the actual, this is the magnetic interaction between the two particles. Okay, so what we want to focus on now is the hyperfine structure. Okay, so before we go on then, are there any questions about this so far?
Oh, good. Excuse me. So what is it that causes that fine structure splitting again? Is it?
It's just the fact that you have an induced field from the orbital motion. This is the spin orbit interaction.
Okay.
That's. So the orbital angular momentum causes an induced magnetic field, and then you can, from that induced magnetic field, it splits the electron. It splits the electron energy. Okay, so now let's work out. What we want to do is we want to find the energy eigenvalues of this Hamiltonian. So now our task here is to find the eigenstates and eigenenergies of this Hamiltonian. Okay, so this is S1 hat dotted with S2 hat. This is now S1x, S1 y, S1, S2x plus S1y, S2y plus S1z, S2z. Okay. So for example, this piece of the Hamiltonian, S1 Z, S2Z, operating on Z plus, Z minus, will just give us, I'll have a factor of plus h bar over 2 here and a minus there, since it'll be minus h bar squared over 4, Z plus, Z minus. Everybody see that? All right, so let's, we can simplify our eigenstates. So let's, in order to just make this a little simpler, so let's define some matrix representations for our eigenstates, which, let me just everybody know what I mean by this? That just saves me some writing. Yeah. Okay, so let's call this 1, 2, 3, and 4. And then we'll let 1 be, we're just going to do this in the easiest possible way. we've defined now these are our base states in the Z basis. Sorry. Z basis. It's just our Z basis representation of the states. All right, now, let's define some ladder operators like we did before with our X and Y operators. So that means S1 plus will be S1X plus I S1Y. And S1 minus would be S1X minus I S1Y. And then S2 plus should be S2X plus I S2Y. And S2 minus so these are just as we have defined the ladder operators previously, except now we have one for plus and minus, or for particle 1 and 2. Okay, so what we're, one of the things we want to do is, if this operator S1 dot S2, we know if these are our basis states here, we know how to handle this part of the operator. That's easy because SZ just gives us H bar over 2 with a plus or a minus. But we don't know how to, we want to have some cleaner way to handle what these operators are going to do on these states. Okay, so what we want to do, so we want to find the matrix elements we want to find the matrix elements between each of these kets, which are, of course, these things. So we want to find a way to rewrite this S1 dot S2 and get rid of these S1X's and S2Ys and replace them instead with the raising and lowering operators, because we know what the raising and lowering operators do. So let's calculate. So let's get rid of, or let's write S1 dot S2 without S1X, S2X, S1Y, S2Y. So to do this, we shall calculate S1 plus S2 minus. Okay, so what's this? Make sure we have enough room here. So S1 plus, this is S1X plus I S1Y times S2 minus. That's S2X minus I S2Y. So if we multiply these out, we'll have S1X S2X. And then we'll have plus S1y, S2y, so these are the things we don't want. But then we'll have let's see, we'll have a plus I times S1y, S2x minus S1 minus S1x, S2y. Okay? You guys are making sure that I'm not making any mistakes here, my algebra. So let's do S1 minus S2 plus. So S1 minus S1x minus I S1y times S2 plus, which would be S2x plus I S2y. And again, we'll have S1x S2x plus S1y S2y. And then we'll have plus I S1x S2y minus S1y S2x. Okay? So, let's see what we have here then. These two, I hope, will cancel out. So we have S1x S2y, I've got a minus sign here, I've got a plus sign here, and then an S1y, S2x. So this term cancels, if I add these things, these cancel. So that means S1 plus S2 minus plus S1 minus S2 plus is equal to twice S1x S2x plus S1y S2y. Okay, so we can get rid of them. I can swap this with these ladder operators. So that means we can write twice. Thus, we have 2 times S1 dot S2. So I'm just going to multiply the whole thing by 2. So 2 times this first term, we know what that is. That's going to be this. This will be S1 plus S2 minus plus S1 minus S2 plus, and then plus the twice S1z S2z. Okay, so now we can actually compute things easily. All right, are there questions over that, just what we did there? Okay, so now what? Well, H was twice A over H bar squared, right? Times S1 dot S2, so let's put the 2. Okay, that's H. So it's just, so this is just then A over H bar squared times S1 plus S2 minus plus. Okay, and we've gotten rid of now we've gotten rid of the S1x, S1y, and so on. So now let's just start calculating. So let's look at, so 1, the ket 1 here is z plus z plus. So if we look at this times Okay, that's the first matrix element that we have to calculate. All right, so which terms here go to 0? Which terms go to 0?
I wanna say the ladder operators, but I don't know.
Okay, well, I guess if it's S1 plus S2 minus is gonna take Z plus to raise or lower the Z plus to Z minus?
If it's a minus, yeah, if
If
it's a,
it's S1 plus S2 minus lower Z plus to Z minus. I don't know if we got that right.
well, what does Z plus do on, this is the spin 1/2.
Oh, right.
What does Z plus, what does
So-
S1 plus do on the first, on Z plus?
Makes it 0.
Right.
A plus on a plus is 0, a minus on a minus is 0.
So is only the last term stick around?
Right.
Yeah.
This plus here, this 2 minus is fine, that'll just turn this into a Z minus.
Yeah.
But this S1 plus will try to raise this, and it can't,
Oh, that's,
so it'll kill it. So that goes to 0, and then the same thing on the second term, this S2 plus goes to 0.
Right.
So we're only left with
Okay.
the Z operators, which are easy to evaluate, so that's, and they're both plus, so we have 2 times H bar over 2, H bar over 2. So this is just, A over 2.
I guess I was wrong.
Sorry, did you say something?
I said I guess I was right then, because I said the ladder operators. I think you're going. Like I'm guessing it's the ladder operators, but I don't know why.
Uh-huh. Okay, so let's try another one. So H here, this is our matrix representation. Let's see, we have A over 2 here, and now we have, 4 times 4, we have 15 more to do, okay? So let's see, I mean, if you go back to the operator here, it's kind of easy to see which ones will be, well, first let's take a look at, well, let's see. Yeah, let's just try to calculate a couple more. I don't want to
Are
go through the
we
entire.
hoping for a lot of zeros or?
There's a lot of zeros in there, yeah. But we should calculate another one that's non-zero. So let's calculate 2 and 3. So that's 2, I just erased it. Let's see, 2 was plus minus. And then we have H, all of that. And then 3 was Z minus, Z plus, right? Okay, so now just any time that, if H was, if the part of H that's just the Z, the S1Z, S2Z, these things don't change the ket at all, right? So if that's the only thing that's left, like if the ladder operators kill the whole thing, or if those terms die, then these things are all gonna die because the ket's not gonna be changed by SZ1 or S1Z or S2Z, right? So this is gonna, these two things will kill each other and these two things and so on. Okay, so that's why a bunch of these things are 0. But anyway, so what is this? So, we have S1 plus S2 minus. So if I S1 plus this guy, that's Z plus, and then S2 minus this guy, that's Z minus. That thing will have overlap with Z plus Z minus, it's the same kit. So that's gonna provide a contribution. So we know that there's contributions from plus and minus. There's no contribution from S1Z, S2Z, and then again, there's no contribution from S1 minus S2 plus. Because S2 plus will try to raise this ket. So this is just Z plus, Z minus, S1 plus, right, S2 minus. Okay, so what did the plus operator give? It was just H bar, right? Yeah, S plus was just to remind you. S Z hat on Z plus is just H bar Z plus, or sorry, S plus Z minus is H bar Z plus, and S minus Z plus is H bar Z minus, with the rest 0. So that means we'll get one H bar from this and one H bar from that. So this was A over H bar squared. So this is A, just A.
Right on that line right above that, was that supposed to be an S2 minus or is it an S1 minus?
Oh, yeah, S2, S2.
So, wait, why is the two S1, S2 contributing in that one, but it's not contributing in the other one?
Because these kets are the same.
Oh, it's the other the same, okay, got it. Oh yeah, they're different, maybe if they're different on the ends, something changes.
Right.
Yeah, okay, got it.
Because this won't change. It won't raise or lower anything.
Gotcha.
Okay, so that's A. And let me fill out the rest of the matrix here so we can. So we have A over 2, 0, 0, 0. There's an A over 2 in the lower corner. 0, 0, 0. And then we have minus A over 2A, A minus A over 2. And then the rest are zeros. So if you calculate them, that's what you'll get. Okay. All right, so now all we have to do is calculate the eigenvalues and eigenvectors of that matrix. So I need the determinant of this, of H minus I lambda, right? To get the equation in lambda that we need. So this will be, let's see, let's let alpha equal A over 2, so I don't have to deal with the factors of 2. So this matrix will then be, or the determinant that I want, will then be alpha minus lambda 0, 0, 0, 0 minus alpha minus lambda, A 0, 0, A minus alpha minus lambda 0, and then 0, 0, 0, alpha minus lambda. Okay, Okay, so this is alpha minus lambda. And then I have to take the determinant, the subdeterminant here, but I can do that starting from here. So this is alpha minus lambda, and then times the determinant that's left over here. So this is minus alpha minus lambda squared minus a squared equals 0. So we have alpha minus lambda quantity squared times, I can just pull out, I can pull out a minus out of there completely. This will just be alpha plus lambda squared minus a squared. So this means that I have one solution is lambda equals alpha twice. And then this solution is alpha plus lambda, this is minus, is equal to plus or minus a. So lambda is equal to alpha minus alpha plus or minus a. Okay, so what's this then? So lambdas, this is minus a over 2 plus a, and minus a over 2 minus a. So lambda here is just a over 2, and this is minus 3a over 2. And this is a over 2 twice. So lambda is equal to a over 2, a over 2, a over 2, and minus 3a over 2. Okay, those are our eigenvalues. So we have triple degeneracy here. Okay, so we have to construct the eigenvectors now. So let's focus first on this triply degenerate eigenvalue. For lambda equals alpha, let's find the eigenvector, or we'll find the eigenvectors. So we'll have our matrix here, which is alpha 0, 0, 0, 0, minus alpha a 0, 0, a minus alpha, right? 0, 0, 0 alpha. Okay, and then we have to have just some vector, a, b, c, d. And if this is an eigenvalue, then it's just that eigenvalue times a, b, c, d. And now we just have to work through, see what it tells us. So the top line, we have alpha a equals alpha a, so there's no info there, and there's no info in the bottom line because that's just alpha b equals alpha d. So we can maybe only get something from the middle two lines here. So that's minus alpha b plus ac is equal to alpha b. Minus alpha b. Oh, okay, right, so ac is equal to twice alpha b, but alpha is a over 2. So we have AC is equal to AB, so we have C equals B. Okay, and we don't have any, this middle line will have, it gives you the same thing. You'll have AB minus alpha C is equal to alpha C, so you'll have you'll get the same relationship there. It won't tell you anything, or it won't tell you anything new. It will tell you B equals C again. So this is all we know. All right, and so now I have to construct eigenvectors. So the eigenvectors must be of the form, of what form? They must be of the form A. I don't know anything about A. It didn't tell us anything, or D. So those two things I don't know. The only thing that we do know is that B must equal to C, so we can, it looks like this. All right? So what should I do now? What are we after? What do I want to do?
Well, okay, so could we want to identify the eigenvectors. Could we do lambda equals minus 3a over 2?
That'll give us a different
Okay,
eigenvector.
they're different, okay.
What should we do here? We need 3 eigenvectors. What freedom do we have?
Can we set them to 1?
Well, we have, what freedom do we have here? Does it matter what value we set for A?
No,
No.
because it can equal anything.
Right, what about D?
And you can set it to 0?
I could.
So
So what do I want though? How many times was my eigenvalue repeated?
3, you have to do it 3 times.
It was 3 times, right? I need 3 eigenvectors.
So you need A or D to equal B.
No, I just need to, I need, of that form, I need 3 vectors that are orthogonal,
Oh, I see, okay.
right? I want them to be orthogonal, otherwise they're really no use to me.
Right, okay.
So just pick the obvious ones.
Right, A over 2.
Hmm?
A over 2.
No, I want 3 vectors that are orthogonal that are of this form. What 3 can I pick?
Just like 1 0 0 0 1 0 0 0 1.
Close, but I can't pick 1 0. I can't pick 0 1 0 0. Why can't I pick 0 1 0 0?
Because the middle ones have to be equal to each other.
B and C have to be equal.
Yeah.
So I can take, let's just take A equals 1 and B equals D equals 0. So then we'll have 1 0 0 0. That's fun. And then we can also do the opposite. We can pick 0 0 0 1. where
0 1
here
1
D is
0
equal to 1.
and 0 1 1 0.
Right, except let's put a 1 over the square root of 2 to normalize it.
Mm.
Okay, those are 3 perfectly acceptable vectors. Okay, so what are they? This is just, this vector is just z plus, z plus.
And the other one is Z minus Z minus.
This is z minus, z minus, and then what's this one?
Oh, it's, yeah, it's the linear combination of Z plus Z minus and Z minus Z plus.
Right. Okay, so we're done with that. So now we only have one eigenvalue left, and that's a over 2, or 3a over 2, minus 3a over 2. So for minus 3a over 2, let's just go ahead and write it out. out here, so we have alpha 0, 0, 0, 0 minus alpha a 0, 0 a minus alpha 0, 0 alpha, operating on a, b, c, d, and this has to be minus 3 alpha times a, b, c, d. Okay, so we should, let's see, what are we gonna find here? Well, the first line is gonna give us alpha a equals minus 3 alpha a. Right, so a has to be 0. And then also we'll get d equals 0. And then in the middle we'll have minus alpha b plus ac is equal to minus 3 alpha b. So I can bring this to the other side, so we'll have AC is equal to minus 2 alpha b, or C is equal to minus b. So this is good, because these two things just have to be different in sign, and so this will be the eigenvector 0, 1, minus 1, 0. Which is 1 over root 2 z plus z minus minus z minus z plus. Okay, so we found everything. I mean, that's good. So let's summarize. So we have 3 vectors. Three eigenpets of energy lambda, which was a over 2, right? A over 2. And then the 1 eigenket of energy minus 3a over 2. So if we look at an energy diagram here, then so there's a splitting. There's another splitting that occurs in the states. So this is minus 3a over 2, and this is 3a over 2. So delta E here is equal to 2a. And in this splitting, due to this hyperfine splitting in hydrogen, this is the 21 centimeter line. Okay, and that's like 1360, what is it? 1420 megahertz. Okay, so if you looked at the hydrogen line, I mean, if you looked at it, you know, you would have so if this were any emission line, you'll have a splitting here that's due to the spin orbit. And then, you know, on top of that, you'll have, you know, more splitting. That's the hyperfine splitting. know, so as you take into account more of these, effects, you know, then you just get, you get more and more accurate answers for the actual eigenstates of the particle. So these things depend on, you know, this is just kind of a rough sketch. These things depend on, there's selection rules, so you can't, there's, you know, photons carry angular momentum, and orbital angular momentum exists for the electrons and atoms. So there are selection rules. You can't, I mean, I have to, if I'm going to emit a photon and go down in energy, you know, for an electron and an atom, I have to go down. I have to also change the orbital angular momentum of the electron in order that the photon can carry it away. So anyway, but this is just like a general idea of what's happening. If I just looked at an emission line, you know, without any resolution, if I could start to look at it with higher and higher resolution, you'd see these splittings that occur just due to these different interactions in the atom. Are there any questions?